Hi, Math 287. This is Dr. Sweeney. This video lecture is going to be based upon the sections 4.1, 4.2, and 4.3. It's vectors and vector spaces. So what we're going to be doing is we're actually going to be doing a video lecture combined with an activity, right, to give you a sense of how it is that vector spaces are kind of put together and how it is that we do things like adding and multiplying by scalars when we're working inside of vector spaces. The vector spaces that we're going to be using inside of this lecture are going to be vector spaces in Rn. Although there are vector spaces that are not necessarily real numbered vector spaces, or also that represent functions, or are things like differential equations, or work with differential equations. And so, consequently, the idea of a vector space is pretty vast, right? It actually is a whole set of groups of objects that it could possibly be anything. I mean, really, there's just a ton of different things that could be vector spaces. They just have to follow a set of rules. The easiest ones to visualize, however, are the ones that we're going to be in Rn, and we're going to talk about Rn in just a little bit. And so what we'll do for these lectures is we're going to focus in on R2. We'll do a little bit of work inside of R3, which is three-dimensional vector spaces. But after that, there's really not a lot that you can do geometry on. So let's begin with vectors in Rn. So what we'll do is, first, we're going to actually demonstrate these things as column vectors. We're not actually going to write them as row vectors. You're going to see that most of the work that we do when we talk about vector spaces is going to be work with vectors, column vectors. All right? And what we mean by a column vector is a vector that's written vertically. Okay? So we're going to call this vector v. And when I'm writing out a vector v, I've got that little slash that's on the top. And I'll set it equal to something, and then we're going to represent this as an n by 1 matrix. So in this case, we'll do a 3 by 1. And so this is 1, 2, 3. Okay? And so we'll write this, and basically, like, x1 is going to be the 1 is in the x1 position, 2 is in the x2 position, 3 is in the x3 position. So we just kind of read them downward. Okay? And if I were to draw, if I were to draw this in 3 dimensions, it would look something like this. I'm going to go in the x direction. I will go 1. Okay? In the y direction, I'm going to go 2. So here's 1, 2 in the y direction. Okay? And then I'll go up 3 in the z direction. And then what I'm going to do is I'm going to draw a line, in this case from the origin to that point 1, 2, 3. Okay? Now, when you're working in multivariable calculus and oftentimes in physics, you understand that a vector, we don't necessarily have to draw a vector from the origin. However, we're going to spend a lot of time drawing vectors from the origin. Because in linear algebra, what's going to happen is that we're really concerned with like the qualities of the vectors and not really where they're going or their products or the values that we get when we actually add them up in space. We're kind of looking at like the generalized form of vectors. So most of the time we're going to be talking about vectors as they're coming out from the origin. Okay? So we'll start out with that. We've got v here. Now, we can, however, definitely go in and draw them out in space. So, for example, if I wanted to let w equal, and we'll have it be -1 to -2, then we could actually just, if I wanted to start out here in space, I could say, okay, well, I'm going to go -1 in the x direction, down 2, or excuse me, not down 2, but 2 in the y direction, okay? And then down 2 in the z direction, and so this vector here would be w as well. And that's an option as well, okay? Now, by the way, I should state, I'm writing this with this being x, this being y, and this being z. All right, just for the purposes of us being all on the same page, okay? And let me end that out. Now, these vectors are vectors in what we call R3. They're called R3 because of two reasons. One, there are three components in the vector. That's the first thing. 1, 2, 3. Three components inside of the vector. And 2, the values in each component are in the real numbers. Now, the geometric representation of R3 is going to be a three-dimensional space, like the one that I just drew right here. However, when we work inside of vector spaces, there are a lot of other vector spaces that have three-dimensional representations that are not R3. And that's really actually quite important. That what makes R3 is these two characteristics right here. Three components in the vector, and the values in each component are in the real numbers. Okay? What you'll see is that we'll, for example, we'll get things called subspaces, and subspaces will be represented three-dimensionally sometimes, but will not actually be in R3 or be R3. Okay? So you want to be very careful. When we talk about R3, we're talking about only three components in the vector, and the values in each component are in the real numbers. Now, we can also talk about Rn, and Rn is very similar to R3, except there are n components in the vector, and 2 is going to be the same as above. The value in each of the components are in the reals. Okay, so that's the second requirement for Rn. So Rn, we have n components, meaning that we can define any amount of components that we want. Okay, and the values in each of the components are the real numbers. So let's take an example. The example that we're going to be using a lot more here is draw a vector in R2. I'll give you a second. Go ahead and pause. And draw the vector. Okay, so your vector should have looked something like this. It'll be V equals the vector 1, 3, or whatever. You might have had 5, 7, 1, 1, 0, 0, 1, whatever it is that you want, okay? As long as there are only two components in the vector and both of the components are a real number. So, by the way, we could have a W and we'll let it equal E pi. That is also in R2 because both E and pi, even though they're irrational, are real numbers. Now let's talk about adding vectors in R2. So we're going to start out with just drawing some of our vectors, and we're going to draw our vectors from the origin. And so we're going to start out with V, and V is going to be 1, 3. Okay, and so what that means is this first component is going to be the x direction. Go 1, and the y direction is 3. So 1, 3, and then what we'll do is we take the vector and we draw it from the origin to that point 1, 3, and so then we say, okay, there's V. That's V. Okay? Now W is going to be 2, 2, and so W is going to go up 2, over 2, and there's 2, 2. And there's W. So we'll go up 2, over 2, and then draw a line from the origin to the vector W. Now, what we're going to need to do now what we want to do is we want to see what is V plus W. So what we're going to do is we're going to do this geometrically first, okay? And then, after that, what we'll do is we will go in and we will, in fact, do this algebraically. It's going to work exactly the way you think it is, and if you've done multivariable calculus, you've already done this before. This is just a review and a refresher. So here's V. We'll draw that from the origin. And then W, we're going to go up tip to tail. And then when we do addition, we're going to do this tip to tail. So we're going to go up 2, over 2. And there's W. The resulting vector, okay? The resulting vector is this vector right here, okay? That vector. And if we look, we can see that it is 1, 2, 3 in the x direction, and 1, 2, 3, 4, 5 in the y direction. So it ends up equaling 3, 5. Now, if you think algebraically, this is going to make sense, because if we go in and we add vectors, like we add matrices, v plus w, excuse me, make it black, is going to equal 1, 3 plus 2, 2, and that ends up equaling 3, 5. And there's our vector addition. Let's take two new vectors, okay? Let's take, for example, we'll take u equal to -1, -1, and w, we'll take w again, okay? Actually, why don't we take t? T equal to 2, -3. Oh, drew u wrong. U is -1, -1, so u is over here, -1, -1. Okay, there's u. And then t is 2, 1, 2, and down -3. 1, 2, 3. There's t. And our new vector, our resulting vector here, is this vector. And it's going to go 1, in the x direction, 1, 2, 3, 4, -4 in the y direction. So u plus t is going to end up equaling -1, -1, plus 2, -3. And that ends up equaling 1, -4, which is exactly what we expect to have. So now I'd like you to try it on your own. We're going to use m and n. So I've got m is equal to 1, 0, and n is equal to -3, 2. Find m plus n. And draw it geometrically. So 1, 0, okay, there's 1, 0, and then -3 is in the x direction, so it's 1, 2, 3, and then down 2. 1, 2, or up 2, excuse me, on 2. And there we are. And there is our vector. And our resulting vector now is -2, -1, 2, and up 2. So it's -2, 2. All right? So m plus n equals -2, 2. Okay? Now, what you want to notice is that each one of these vectors, right, that vectors have length and they have direction. So they're pointing in different directions, and they also have certain lengths. So vectors have lengths and directions. We are actually going to be pretty much interested in the directions only for the purposes of this class. Although the lengths will come into play sometimes, but most of the time we're going to talk about the directions. And we're going to talk about vectors being in the same direction. It's going to be a really important idea. And so you'll see things like, -2, 2 and -3, 3 are in the same direction. Okay, because they lie on what we'll call the same line of direction of vectors. And we're going to talk about that in just a second when we talk about scalar multiplication. Now let's take a look at something called scalar multiplication. And we've done scalar multiplication before. So here's my axis. I decided to do it back in red. Why not? And what we mean by scalar multiplication is we mean what happens when we multiply a scalar, say for example a scalar, call it S, right? A scalar, times V, a vector. So let's take a look. We're going to do one in R2. Let's let S equal 3. Okay? And V, we're going to let V equal, let's have it be 1, 1. Fairly simple. So we start out with V. We make V 1, 1. Okay? And what's going to happen with S is scaling is going to multiply V, or stretch V. by the scalar. So in this case, it's going to actually scale v by 3. So we'll make it 1, 2, 3. We'll triple the length, and that's now what we call SV. Okay, so our new red vector is SV. Our original vector was v. And that's a scaled vector. We're also going to get, say for example, let's let s equal -2, and the negative moves the vector in the opposite direction. The vector in the negative direction, or in the negative direction, right? Okay, and what that means for us is it means it basically flips it over the origin. So let's say, for example, I take SV in this case, which is going to be, or let's call this S2, just to make it clear, S2V, all right? And what it's going to happen is I'm going to start out with V, but then I'm going to flip over the origin, right? Make it -1, 1, and then scale it by 2 in this case, okay? So flip and then scale. And so my new vector, let's make this one blue, is going to now be -2, -2. Okay, it's been flipped over the origin, all right, and then multiplied by, flipped over the origin and then stretched by 2. So let's have you try this. Okay, we're going to try this, and what we're going to try is, let's do, we'll let s equal -5, okay, and we'll have another scalar t equal to +3. Or how about +5? Okay. And then we're going to let v equal to 1. Okay. So draw SV and TV. Go ahead and pause and do that. All right, let's go in, and we're going to first do SV. So we've got 2, 1. So we'll go 1, 2, and up 1. So there's 2, 1. Then what I'm going to do with this vector with -5, remember I'm going to flip it over the origin. So I'm going to go over here. I'm going to end up at, right, 1, 2. And then I'm going to stretch by 5. So here's another. And a second, a third, and a fourth, and a fifth, and so there we are. There's our resulting vector, and all I got to do is I got to figure out what that vector is. It's 1, 2. It's no wonder that didn't look right. Okay, so I'm going to go 1, 2. Okay, so I flipped it over the origin. Okay, and now I'm going to stretch it by 5. And there's my resulting vector. And that has 2, 4, 6, 8, 10, and 1, 2, 3, 4, 5 in the negative direction. So this ends up being, this resulting vector SV is equal to -10, -5. Okay, great. Now let's do TV. T was +5. So we've got +2, okay? And now, so we're going to go, there's our vector v, and we're just going to stretch by 5. 1, 2, 3, 4, 5. Okay, and there we are. And so consequently now, we've gone up 5. 1, 2, 3, 4, 5. Or it should be up 5. And 2, 4, 6, 8, 10. Actually, I went 1 too far. There it is. And that's why I ended up with not the vector that I wanted. And so this vector, now TV, is equal to 5. Or excuse me, 10, 5. And there we go. Algebraically, this makes sense, right? So if I take -5 and I multiply it by 2, 1, what I get is I get negative 10, negative 5. And that's TV. If I take SV, or excuse me, this is SV, pardon me. If I take TV, then I'm going to take 5 times 2, 1, and that ends up equaling 10, 5. And that's scalar multiplication, and that's how that works. The final piece here is this piece called linear combinations. We talked a little bit about this before, but now I really want to get a lot more into linear combinations. They play a huge role in working in vector spaces. So let's say for example we have t equals negative 1. All right, we'll have s equal to 2, and then we'll have a vector v equal to 3, negative 2, and a second vector w equal to 1, negative 1. Or actually, why don't we do negative 1, 2. Okay? Now, our linear combination is going to be vector times a scalar plus a vector times a scalar, or it's a combination of vectors and scalars, right? And that's what makes a linear combination. So, for example, we might have TV plus SW. Okay? So we've got scalar times vector plus scalar times vector. All right? And so this is actually something that, we're going to see a lot of different ways that we can do this. We could have 3 vectors, we could have 5 vectors, we could have 20 scalars. You're going to see things like written very generally in this form, and this is the linear combination form. All right, and so what this is saying is okay, we're interested in the resulting vector. We'll call this resulting vector, we'll call it x. We're looking at that resulting vector, and that we're going to say that x is a linear combination of v and w. So x is a linear combination of v and w. And this is an important idea, okay? Because we're going to ask questions like, is B a linear combination of the column vectors of A, right? Or you want to know what that means, and this is what it means. It means, can I write X as a linear combination, right? Some scalar plus times the vector plus scalar times the vector of a set of vectors. Actually, I shouldn't, that's defining that as a scalar times vector, etc., for a set of vectors. And that's what I mean. Now, geometrically, what a linear combination looks like then, let's say, for example, we did do TV. We'll start out, and I'm going to make this first vector TV with red. V is 3, 2, so this is 1, 2, 3, and negative 2, 3, negative 2, okay? Then we'll go in and we're going to scale it by negative 1, and so what that means is that we're going to flip it over the origin. We're going to move it in the opposite direction, all right? So this vector right here is TV. There's TV, okay? And now we want to do that, and then we have SW, so we're going to add to it SW. So W is negative 1, 2. So negative 1, okay, negative 1, 2. There's that vector. Okay, we're going to draw it tip to tail because we're adding SW. Okay, so there's W, and then we're going to multiply it by 2, so we're going to take 2 of those. And there we go. And actually, let me change that color. We're going to change it to blue. And our resulting vector now, okay, is in fact the x vector that we're looking for. Okay, so here is SW, okay, and here is x. And so x is 1, 2, 3, 4, 5. That's negative 5. 1, 2, 3, 4, 5, 6 is x equals negative 5, 6. Geometrically, assuming that I've done everything correctly. All right. Now if I go in and I write it, I'm going to do my work, TV plus SW. What we'll do is we write this, we say -1, we write the scalar on the outside, times 3, -2, plus, okay, 2W, excuse me, which is 2 times -1, 2. And then in general, although we don't actually have, well, in general what we'll do is we'll then scalar multiply. So this becomes -3, 2, plus -2, 4. And this ends up equaling, when we add them together, -5, 6. Okay? And that's how we do scalar multiplication. That's how we actually write linear combinations, by combining scalar multiplication and vector addition. Super important, really, really valuable. Okay? So let's try this. I'll have you try one on your own. We're going to let S equal to -3. And we're going to have T equal to 1.5. So we'll actually write it as a fraction. Okay, so you're going to take 1.5 in this case. And we're going to let V equal -2, -2. And we're going to let W equal 4, 6. So go ahead and draw, and then find algebraically. SV plus TW. So go ahead and pause your video and find SV plus TW. So we'll start out with W or SV. So we set V, that's -2, -2. Here's my vector V. Okay. And S is going to be -3, so I'm going to flip it over the x-axis, or excuse me, over the origin. And then I'm going to stretch by 3. So there we are. There's SV. And then TW is going to now be, all right, we go 4, 6. So 1, 2, 3, 4. Up 6. 1, 2, 3, 4, 5, 6. Okay. So there's that. There's the second one. Oh, I've got to go into, I'm stretching way beyond. But what we're going to do is we're basically just going to take another half. Because we're going to go up 1.5. And so there is, this whole thing here is TW. And my resulting vector, this vector right here. Okay. And so that resulting vector, let's just actually do the algebra. It's going to be -3 times -2, -2, plus 1.5 times 4, 6. Okay, and it should be pretty darn close to being right on y equals x, although it's not exactly. And so this is going to end up being 6, 6 plus 6, 9. And so that ends up equaling 12, 15. And that is our resulting vector. 12, 15, that's my resulting vector. That's the linear combination. Okay? So the final piece for the beginning of our talk is going to be these things that we call the standard basis vectors. We're going to get into what a basis is a little bit later, but what we want to get is that these are what we call the most fundamental, or the most, the simplest of vectors in order to write linear combinations with. Okay? So like, we're going to use these, we're going to call our first standard basis vector, we're going to call it E1. Okay? And in R2, it's going to be 1, 0. And so it'll represent a unit vector, if you remember that from multivariable calculus, a unit vector, a vector of length 1, okay, on the x-axis. And in many ways, it's in fact going to be like a stand-in for the x-axis. Then we're going to have E2, okay, and that's going to end up equaling 0, 1. Okay, 0, 1. And so that is going to be basically a stand-in for the y-axis. It's a unit vector on the y-axis. The thing is that what we can do is we can write any vector on the x-axis. Okay, so any vector on the x-axis as a scalar multiple of E1. So we call that SE1. Okay? So, 2E1 is just 2, 0. Negative 5E1 is negative 5, 0. Okay? You can kind of, see, negative 2 times 1, 0 is just simply negative 2, 0. Right? Okay? And any vector on the x-axis, or excuse me, on the y-axis, and we'll call it, we're just going to use t, but it's still s. Actually, let's just use s, E2. And so that's the second standard basis vector. Okay? And so, say for example, I want to do, I don't know, what is that? 1, 2, 3, 4, 4.5. 4.5 E2 is going to end up equaling 0, 4.5. And so those are the standard basis vectors. The great thing about standard basis vectors is that we can easily write any vector as a linear combination of them. So any vector in, say for example, R2 can be written as a scalar multiple of E1 and E2. Or excuse me, as a linear combination of E1 and E2. So that linear combination of E1 and E2. So for example, if I wanted to write 5, 3, the vector 5, 3 is 5 times 1, 0 plus 3 times 0, 1. And so basically these standard basis vectors are going to be the simplest way for us to write linear combinations. Now there are going to be a lot of other sets of vectors that we can write every other vector as linear combination, but these standard basis vectors are going to be the easiest ones. So go ahead and try this out. Write negative 2, negative 3 as a linear combination of E1 and E2. All right. So should be negative 2 times 1, 0 plus negative 3 times 0, 1. And you can see that that's equal to negative 2, negative 3. Now, R2 isn't the only thing that has a standard basis, right? Let's take a look at the standard basis for R3. So if we take a look at the standard basis for R3, it's going to have E1 equals, and we're just going to have a 1 and 0, 0, 1 in the first component, and that's what makes it E1, by the way. It's in the first component, that 1. E2 is going to equal 0, 1, 0, 0, 0, 1, 0, and E3 is going to equal 0, 0, 1. Okay? So now, let's say, for example, I want to write the vector negative 2, 5, 1 as a linear combination of these vectors, okay, as these standard basis vectors. I'm going to write it, I'll write it as negative 2 E1 plus 5 E2 plus 1 E1. And what you'll be able to see is you'll see, oh, okay, well that's negative 2 times 1, 0, 0 plus 5 times 0, 1, 0 plus 1 times 0, 0, 1. And that ends up equaling negative 2, 5, 1. Okay? If you think about this geometrically, it makes a lot of sense. All right? We're not going to do this one three-dimensionally. Let's take a look at one of the two-dimensional vectors. Okay? Let's say, for example, we did this first one here, the 5, 1, 0 plus 3, 0, 1. Okay? So you take 5, 1, 2, 3, 4, 5. Okay? We go out 5 on the x-axis, and then we're going to go, here's 1, 0, 1, and then we'll stretch that up by 3. So there's that. And our resulting vector is exactly where we expect it to be, right? Those standard basis vectors, geometrically, they draw triangles. And so consequently, they're really easy to visualize as well. So they've got easy visualization. They've also got easy computation, okay? And we know, what you can do is you can actually, and we'll do this later, is you can show that any vector in, say, for example, R2 can be written as a linear combination of 1, 0, and 0, 1, okay? And any vector in R3 can be written as a linear combination of E1, E2, and E3, okay? And basically what these bases are is the bases are going to be ways of writing every single vector in whatever vector space you're working in as a linear combination of the standard basis vectors.